This is the continuation of section 9.3. So our next example, when talking about p-series test, we're supposed to look at this one. Sigma from n equals 1 to infinity of 1 over n to the pi. Well, pi is a number, so yes, this is a p-series. It's in the form 1 over n to the p. So you write down that you're using the p-series test by just writing p-series. Then identify what p is. In this problem, it's pi. And then you say, since there are two statements to choose from. You're either going to write p is greater than 1, or p is between 0 and 1, including 1. Well, pi, which is 3.14, is a value of p that's greater than 1. That implies, therefore, that this series, sigma n equals 1 to infinity of 1 over n to the pi, converges. Short and sweet. I like this. This is really good. P-series and geometric series are probably the easiest. Well, unless the nth term test tells you you're getting something that's not 0, and then you can just say, well, then it diverges. But anyway. Let's see. All right. Well, that is not a p-series because it's ln of n over a power of n. That's not the p-series. And we've actually done other things before this, so we have to think about what it can be. I'm seeing something I think I can integrate. So I'm going to talk about the function f of x, which is ln of x over x squared. It's positive. Well, see, the natural log of 1 is 0. So it's not going to be positive when x is 1. So let me make a statement up here to help you. If you have an infinite series, and let's say you have a plus b plus c plus the rest of it, and if I can prove that this converges, that means it converges to some number. I may not be able to find that number, but I can tell you that it does converge to something. And if that something is added to a plus b and c, 3 constants, that's going to be a number as well. And so this series would converge even if these first 3 don't do what I want as far as the conditions of the test are concerned. So the statement I want to make is that the first few terms, few is a relative, oh wow, that looks so awful, let me try again. First few is a relative term here. Okay, the first few terms of a series do not affect a series convergence or divergence. So if the first few terms aren't well behaved, But we can conclude that starting, let's say, the fourth term, that from the fourth term on it converges. Then take that sum, even if you don't know what it is, and add to it a and b and c, then it will converge. By the same token, if you can prove that starting with the fourth term it diverges, which means it probably goes to infinity or negative infinity, if you add a, b, and c to infinity or negative infinity, it's still going to be infinity or negative infinity. So the first few terms of a series can be ignored when you're trying to match the conditions for a test. So it's not positive at x equals 1, but I'm going to say it is after that. So, and it is, because the natural logarithm of a number bigger than 1 is positive, and x squared is positive. So that quotient is definitely positive. Okay. Continuity. You can't divide by 0, so x can't be 0, but since we're starting after 1, that's not a problem. So it's positive, it's continuous, and it's decreasing. And let me see just a second. We can prove this is decreasing using the first derivative test. But this time I'm just going to wave my hands and say I really don't want to do it this time. Let's pretend like this is a problem on the test where I said you must use the integral test. Now this time the interval doesn't include 1, but so we're ignoring that first term on purpose, and that's perfectly fine to do that. It's no big deal at all. So what we're supposed to do then is set up the improper integral. Oh, I've got to say the integral test applies or something like that, because that's what we were trying to determine. Even if I tell you to use the integral test, you got to tell me those three things are valid and that the integral test actually is applicable to that particular problem. Okay, so we set up the improper integral from 1 to infinity of natural log of x over x squared dx. Alrighty. So to do this one, I of course got to change first the improper integral into a limit of a definite integral from 1 to b as b goes to infinity. If you don't mind, I'm going to go ahead and algebraically change that into x to the negative 2 multiplied by ln of x. So I don't take an extra step just to do that little bit of algebraic mumbo jumbo. All right, so let's see, that's a product of functions, and I seem to recall that we talked about a technique to do that. It was called integration by, do you remember? By parts. And in doing that, we have to figure out what's u, what's dv. And we're going to find dv by paying attention to detail. The d is for dv, so we're going to find dv by looking for first an exponential function. There's not one of those here. There's no 2 to the x or e to the x here, so nope. Detail is trigonometric. Nope. A, algebraic. Yep. X to the negative 2 is an algebraic expression. Dx always goes with dv. So whatever's left is u, and that's ln of x. So then you find du. The derivative of ln of x is 1 over x dx, and du always has a dx associated with it. And v is the antiderivative of dv. So that's going to be x to the negative 1 over negative 1, aka negative 1 over x. So this is the limit as b approaches infinity of, okay, the first thing is u times v. So v is negative 1 over x times u. That's the order I'd like to see that in, generally speaking. Algebraic before the logarithmic. So uv minus the integral of v du. V is negative 1 over x, and if I pull that negative out, it turns that into plus 1 over x. That's v du, which is 1 over x dx. Okay, now I've got to go back and think about this carefully. The integral is still from 1 to b, and the thing I forgot to put in when we're doing the definite integral with integration by parts, the first part is out of the integral, so I need to put that from 1 to b for the part that's already out of the radical. I'm actually not going to evaluate it yet, but that's technically on the first part that has to be from 1 to b since it's out of the radical. Okay, so I think of that as the opposite of ln of, oops. Actually, I think I will go ahead and start evaluating it. Since we're here, we might as well. So this is going to be negative natural log of b over b minus negative natural log of 1 over 1. So we're going to need another grouping symbol here. Plus, okay, and this is the integral of x to the negative 2 dx from 1 to b. Now what I'm not going to do is I'm not going to evaluate the limit yet. I'm going to wait till I've done all of the integration and substitution and do this limit process all at the end. So I guess I'll put this here. So negative natural log of b over b. Natural log of 1 is 0, so that'll end up being minus negative, so plus 0 over 1 is 0. Plus the antiderivative of x to the negative 2. Well, that's what we did in our integration by parts, isn't it? So we already know what that answer is. It's negative 1 over x. And that will be evaluated from 1 to b. Well, it's so nice when your own work comes back and helps you. As long as you did the first time correctly, you can sure save yourself a lot of time. Okay, so this is going to be, actually could have used parentheses, the line above. Oh well. All right, so this is going to be negative 1 over b minus negative 1 over 1 okay. Let's see. Well, as b changes to infinity, the negative natural log of b is going to, well, the natural log of b is going to infinity. So negative infinity over infinity, I think I'll have to use the L'Hopital's rule for that. So since b is a value of x, and we are talking about a function already, we can certainly just go ahead and use L'Hopital's rule, because that first term, at least, is negative infinity over infinity. So by L'Hopital's rule, that will become the limit as b approaches infinity and the derivative of negative natural log of b is negative 1 over b, and the derivative of b would be 1. We're treating b as if it were x. Now, one thing you got to be careful of here is that only that first term, the negative natural log of b over b, is negative infinity over infinity. The rest of it, I'm going to go ahead and evaluate that limit over on the right. So the limit of negative 1 over b as b goes to infinity is 0. Minus negative 1 is plus 1, and the limit of the constant 1 is 1. Okay. Then, going back to the first term, that fraction, negative 1 over b as b goes to infinity, goes to 0. So 0 plus 0 plus 1 is 1. And that means that the improper integral of ln of x over x squared dx does what? If you get a real number, that means that the improper integral converges. And since the improper integral converges, what does that mean about our series? Well, because of that theorem, the integral test idea, that means that the related series ln of n over n squared as n goes to infinity also converges. You may have heard me say before in this class that anytime we do a problem, it's very likely that we're going to have to use skills from a prior course or even prior work that we've done in this course. So this is a nice little review of integration by parts, as well as the integral test being a nice review of improper integrals. So it's always good to make sure that you still know stuff, even from this course, because the final will be a cumulative test. So that's kind of a good thing to keep your eye on. All right, this one, n over n to the 4th plus 2n squared plus 1. Well, this is not a p-series. It's not 1 over a power of n. So the only other thing I might think about was first is as n goes to infinity, what will that expression go to? Well, n over n to the 4th basically is going to go to 0. So that's inconclusive. If I gotten something not 0, I could say it diverges, but I don't think I'm ready to say that yet. Dang. So let's consider the integral test again, because that's what this section is about, is p-series and integral tests. So we're going to have a little bit of both in these last examples. This one I think we can do with the integral test. We'll see. Well, you might notice, and I kind of hope you do, because it really helps in this problem, you might notice that that denominator factors to be x squared plus 1 squared, which is really going to make this problem go. So that's what we're going to let f of x equal. F is positive. If x is 1 or bigger, the numerator is positive, and the square of any denominator we might come up with inside the parentheses will be positive. So it's definitely positive. There are no numbers that make x squared plus 1 equal 0, so it's definitely continuous. And again, I'm going to wave my hands and say that we could do the first derivative test. In fact, I'm going to jump kind of halfway into that and just pretend like we've already done some of the work, because this one is kind of interesting. So pretend like we've found the first derivative using the quotient rule, and we ended up getting this. Oh, rats. Sorry. That was a different problem that I wanted to do that with. My apologies. I was looking at the wrong one for a second. So we're just going to wave our hands this time. Let's just say it's decreasing on the interval 1 to infinity. All right, so the integral test applies. So we use the integral test. You notice there are some things that I will abbreviate, and you're welcome to do those same abbreviations. There are other things like the names of tests that I really don't want you to abbreviate because I want you to make sure you know those full names. Okay, so we set up the improper integral for the function x over x squared plus 1 as x goes from 1 to infinity dx. So we rewrite that as the limit of the definite integral from 1 to b as b goes to infinity of our function of x dx. All right. Well, I'm glad I factored that because actually that's really critical for this problem because u is x squared plus 1, which means that du is 2x dx. And luckily we have the x and we have the essential dx. So x is essential and dx is essential. The only other thing we have to put in is the 2, and that's something we can put in as a constant multiplier by multiplying by 2 inside and its reciprocal 1/2 on the outside. Okay, so that's the limit as b approaches infinity of, and at this point we really don't want to change the variable on improper integrals. So a lot of times you'll see me going off to the side and dealing with just the antiderivative part. So the 2x dx is my du, and the x squared plus 1 is my u. And that's the integral of u to the negative 2 du, which is u to the negative 1 over negative 1, negative 1 over u plus c. So going back to this problem, don't forget that constant 1/2 that we introduced. That still has to come along. That's going to be multiplied by negative 1 over u, which is x squared plus 1. So in the flow of the problem, we never went to u. We did that u substitution and that thought process over to the side. Anyway, so we get that is our antiderivative evaluated from 1 to b. So this is the limit as b approaches infinity of negative 1 over 2 times the quantity b squared plus 1 minus negative 1 over 2 times the quantity 1 squared plus 1 okay, And that first fraction, as b in the denominator goes to infinity, the denominator goes to infinity, and any constant divided by an infinitely large thing is headed towards 0. Minus a negative is positive, and that denominator ends up being 4, so we get an answer here of 1/4. Okay, so that answer means, of course, that our improper integral, because we got a real number here of x over x squared plus 1 quantity squared dx, since we've got a real number, that means that the improper integral converges. And then using the integral test, which we referenced above, so I don't need to say it again, means that the series that we wanted to start with and find its convergence or divergence has now been proven to also converge. So that's that one. Okay, last example in this section. Okay. This is n over n squared plus 5. Not a p-series because it's not in the form 1 over n to a number. So that means that we're probably supposed to try the integral test. Because it's in this section, you kind of know that that's what you should try. If x is 1 or bigger, the numerator will be positive. The denominator is positive anyway, so that means that f is positive as long as x is going from 1 to infinity. It's continuous because x squared plus 5 cannot be 0 with a real value of x, and it's decreasing. Actually, I want to prove that sort of. This is the one I accidentally jumped to. I'm going to pretend like you did the quotient rule and found f prime and got that correct, because I want to jump to this conclusion that we get from it. So this is 5 minus x squared over x squared plus 5. Oops. Quantity squared. Okay, so when is that equal to 0? Or when does it fail to exist? Well, the denominator will never be 0, so the non-existence of the first derivative never happens. Okay, the only way this fraction can equal 0 is if the numerator equals 0, which means that 5 will equal x squared. And so x is plus or minus the square root of 5. So we have two critical numbers, negative square root of 5 and positive square root of 5. These were obtained by setting equal to 0, so we put dots there. If it had been from doesn't exist, we put an open circle. This is the first derivative number line test, and the sign that we get for f prime will inform us about what's going on with the function in each of these three parts of our domain, of the real number line, I should say. So if I picked a number that's to the left of negative square root of 5, like negative 10. Negative 10 squared is 100. 5 minus 100 is negative. The denominator, since it's the square of something, will be positive. Negative divided by positive is negative, which means the function is decreasing in that part of the domain. Something between negative square root of 5 and square root of 5, I like 0 for that. 5 minus 0 squared is positive, divided by always positive is positive. And then finally, if I put in a number like 10, we'll get the same result as if it were negative 10, because 10 squared is 100, 5 minus 100 is negative, divided by always positive is negative. So that means the function is decreasing there and increasing in the middle. Okay, well, don't have the square root of 5 memorized. I know it's bigger than the square root of 4, so it's bigger than 2. Square root of 5, just picking up my calculator here. Square root of 5 is approximately 2.236. So, as it turns out, it is decreasing after x is 2.236. And of course, since we're relating this to n and n is a positive integer, I'm going to be able to say it's decreasing, but not starting at 1. It's not decreasing then. From negative 2.2 to positive 2.2, it's increasing. So what I'm going to say is that it's decreasing when positive and continuous on the interval from 3 to infinity. Okay? So it's okay to ignore the first few terms of that series. It won't affect the convergence or divergence of that series. So I wanted to do this one on purpose just so you'd see that it's not always going to be decreasing for the first few terms, and this is how you'll deal with it. All right, so our task then is to set up the improper integral from 1 to infinity, despite the fact that it's increasing between 1 and 3. We still set up the improper integral from 1 to infinity of our function x over x squared plus 5 dx. So we'll rewrite that as the limit as b approaches infinity of the definite integral from 1 to b of x over x squared plus 5 dx. So if I let u equal x squared plus 5, du is 2x dx. The only thing I don't have in my integral is the 2. So you've seen this before, so this is no big deal. Easy peasy. And the integral we're doing is going to be the constant in front multiplied by the antiderivative of 1 over u du. That's the form this is in. 1 over u du is the natural logarithm of the absolute value of u evaluated from 1 to b. Now, if you needed to go off to the side and write down the lemma integral of 1 over u du equals natural log of the absolute value of u plus c, and then come back here and write natural log of the absolute value of x squared plus 5, that's fine. But I'm thinking some of these are easy enough, and you start seeing them enough where you don't have to go off to the side as much, and you can just do some of that in your head. All right, so this is going to be 1/2 of the natural logarithm of b squared plus 5. I don't need the absolute value because x squared plus 5 cannot be negative, and that's the only, well, that and 0 are things that we want to avoid, and that won't happen with b values between, I'm sorry, x values between 1 and b, which is headed towards positive infinity, minus 1/2 natural logarithm of 1 squared plus 5 is 6. Okay, the first part of this, as b goes to infinity, b squared plus 5 goes to positive infinity, and as the input for natural logarithm grows, the output grows without bound to positive infinity, and positive infinity minus that little constant is still positive infinity. So what we've shown is that the improper integral of x over x squared plus 5 dx diverges. But make sure that you say this statement, and then you've got to go on and actually answer the question that was posed. What about the series? Well, because we use the integral test, whatever the improper integral does, that's what the series will do. So that means that the series, sigma from n equals 1 to infinity of n over n squared plus 5, also diverges. Okay, that's the end of this section. I will see you in class.